For those who have joined, we'll just give it one more minute before kicking things off. Okay, I think I can start with some introductions. So welcome everyone. I can't actually tell how many people are joined in from home, but hopefully expecting some good numbers today. Um, Really a pleasure to introduce this event. As it says on the screen, hopefully, if I'm sharing correctly, this is a event that is talking about applied seismic retrofit experiences from Canada and New Zealand. This is an event that that Swanand and I are co-chairing. Swanand is our iStructD representative on the SecEd committee, and this talk is a co-badged event between the iStructD and SecEd. Um, Before I get on with introducing further the talk and the speakers tonight, just to go through a couple of upcoming events in the SecEd calendar. Um, we have a sort of lunchtime event or lunchtime UK time, but you can join whenever that works out for you, time zone wise, on Teams on the 10th of April. That's at 12:30 till 1:30 UK time. And that's on risk sensitivity to hazard model updates, insights from the European seismic hazard model. Um, so that's an event organized by our Young Members Committee, and as I say, the 10th of April. Towards the end of April, the 30th, we have our annual general meeting of SecEd and also EFIT. If you're interested in both EFIT and SecEd, you can come along at 6 o'clock for the EFIT AGM to be followed by the SecEd AGM at 6:15. This is held in person at the ICE. It will be also broadcast virtually like this one, but for those who can make it in person, you'd be very welcome at the ICE. And that will be succeeded at 6:30 UK time by a talk about the EFIT from the EFIT team that went to the Morocco earthquake to Morocco after the earthquake in September 2023. So as I say, that event is on the 30th of April, 6:30 p.m. That will be held in person at the ICE and is a hybrid event. And that is co-badged with EFIT, of course, as well. The speakers coming from that EFIT mission. Finally, this has been announced at previous SecEd talks, but just to continue to get the word out there, we have our biannual prestige lecture, the Mellon Milne lecture. This is the 19th Mellon Milne lecture. Really excited to have Professor Calvi from the University of Pavia in Italy coming over to talk to us about risk management and rehousing of people displaced by earthquake disasters. Really sort of a helicopter view of his career, really, in terms of work he's done on risk assessment, seismic retrofit of buildings, base isolation, and in particular, learning lessons from the L'Aquila earthquake in 2009, where he played a big role in the reconstruction there. So really looking forward to that event. As usual, that will be held at the ICE in person as well, and it will also be available online. And that will start, I believe, at 6 o'clock at the ICE, and it will be followed by a drinks reception. Watch your email for notifications about getting tickets for the drinks reception. I can't recall the ticket price, but it's a modest price for the opportunity for the networking. Um, so on to tonight's event. So I've already mentioned that this is a co-badged event with the iStructD. We've actually been sort of looking to get a talk on seismic retrofit and co-badge with the iStructD for some time. It's been sort of on the SecEd agenda for a while now. Swanand joining the committee as the iStructD rep has really catalyzed this, and we've got this talk together. And we're really sort of looking at two different, I suppose, a couple of different lenses of the seismic retrofit problem. What the first talk from Dave Arnold will look at a specific retrofit project in Ottawa in Canada. So looking in more detail, I suppose, at the types of practical considerations in carrying out a retrofit of a heritage structure in Canada, the Federal Parliament building in Ottawa, as we'll hear. And then Jared in the second talk is going to, I suppose, take a higher level view of across multiple retrofit projects in New Zealand from his experiences there. Um, Really nice little personal connection for me, this talk. Dave and Jared were both my classmates in Canterbury. So while we have a diversity of topics being presented today, I suppose not a diversity of speakers. Dave is a principal structural engineer at WSP in Canada. And as you'll see, is currently senior technical manager on this project that he's going to talk about. And Jared is a global seismic lead at Beca, the New Zealand engineering consultancy, and has worked on a number of retrofit and other engineering projects throughout the world, both in New Zealand and in time spent abroad. And he's also involved, I believe, in the I forget the name of it, but the Dynamics Task Force that Swanen is also on, and is was the iStructD New Zealand branch chair as well. I think that's enough intro, possibly longer than enough. So I think it's just my great pleasure to first of all hand over to, like I say, my old classmate and friend, Dave Arnold. Take it away, Dave.
All right, thank you, Damian. Let's share my screen.
Actually, while you're just sharing your screen, Dave, I meant to mention that we'll take questions at the very end for both speakers, and we'll use the chat facility as Swanen has just indicated there. So please feel free to get the questions coming in during the talks, but we'll address those at the end. Thank you. Over to you, Dave.
Okay, so hopefully that my screen is sharing okay there.
That's fine. Yep.
Perfect. Alrighty, so as you heard, my name is David Arnold, and I'm a structural engineer with WSP Canada, working on the seismic upgrade of the historic Canadian Parliament buildings in Ottawa. So this project is currently nearing the end of its design phase. However, many aspects of it are already in construction. So in this presentation, I'm going to give a brief overview of the seismic hazard that we face in the Ottawa region, the building and its historic construction. Some of the seismic load path challenges that the building has, and the design solutions that we've adopted for its seismic upgrade. So beginning with the seismicity of the area, in Eastern Canada, the seismic hazard is relatively modest, particularly in comparison to the seismic hazard faced in Western Canada. However, it's certainly not negligible, and the Ottawa region does have a history of magnitude 5 type events, along with some less common magnitude 6s. And what that results in for a short period, unreinforced masonry building, such as the Canadian Parliament, would be a design base shear of approximately 39% of its weight. And we actually had a small reminder about 15 years ago that earthquakes can affect our region's infrastructure. These photos were taken after the nearby Val des Bois earthquake of 2010. So with that said, how common is seismic upgrading in Eastern Canada? Well, it's actually relatively rare and seldom performed outside the context of a larger rehabilitation. And that is also the context for the Canadian Parliament seismic upgrade, which is just one part of a much bigger rehabilitation program. So moving on to the building itself, here it is. This is the Canadian Parliament building. It's commonly known as Centre Block. And it's located on Parliament Hill in Ottawa, occupying a very prominent position overlooking the Ottawa River. It's a majestic building, and it's also a very large building. The length of its south facade, shown here, is approximately 150 meters in the east-west direction, and the building is approximately 75 meters in the north-south direction. The tall tower that you see on the south facade here is known as the Peace Tower, and it's approximately 90 meters tall. So the building was constructed between 1916 and 1920 after fire destroyed its predecessor in the winter of 1916. And it was reconstructed with a one-story concrete basement. Plain concrete was used in the basement walls, but you can see that the ground floor slab was reinforced, making it a relatively early example of reinforced concrete in Canada. Above grade, the building's six-story superstructure was constructed with unreinforced masonry. And the superstructure's floors used these hollow terracotta tiles that form a flat arch spanning between embedded steel beams. There is tie rods, and you can see a tie rod in the photograph there that is built into the mortar joints between the terracotta tiles. And one of the primary motivators for selecting this type of floor would have been its excellent fire resistance, which would have been front of mind during Centre Block's reconstruction. And from the historic photos, we can see that Centre Block's reconstruction was really quite rapid, with the majority of the structure complete by about the end of 1918. That's only 3 years after the fire. Completion of the interior finishes followed along after this, as did the Peace Tower construction, which was finally completed in 1925. You can see in this photo that the Peace Tower was constructed with plain concrete with an exterior weight of sandstone masonry. Inside Centre Block, its interior finishes are highly decorative. It has some spaces with ornate vaulted stone ceilings. This example is a room immediately behind the Peace Tower, known as Confederation Hall. And leading from Confederation Hall to the Library of Parliament beyond is the Hall of Honour. And Centre Block also has many rooms with elaborate plaster ceilings, which were constructed by applying plaster to a hanging cementitious slab. This is the reading room, again with a hanging plaster ceiling attached to a suspended cementitious slab. And in Centre Block's lower levels in particular, the walls are typically lined with a decorative withe of limestone. This is a level 2 corridor. You can see the marble floors. This is also on level 2. It's the lobby outside the Senate chamber. It has a beautiful ley-light structure, providing natural light to the space below. So what are the key seismic load path challenges for the building? Well, firstly, the building's unreinforced masonry walls have been assessed to meet less than 30% of code. That's the National Building Code of Canada. In addition, the building's hollow terracotta tile floors do not really provide a rational horizontal seismic load path due to their poor connection to the building's walls. The building also contains many heavy non-structural components that could pose a significant life safety risk in a seismic event, like those vaulted stone and suspended plaster ceilings that I showed. It also has 4 towers. I'll show you some slides of those later in the presentation. 4 towers at the rear of the building that have inadequate lateral strength, as does the Peace Tower on the south facade. So to address these deficiencies, the key seismic upgrade measures that we've decided on are, number 1, implementation of a basement level seismic isolation system, strengthening of the building's hollow terracotta tile floor diaphragms with a thin UHPC, that's ultra high performance concrete topping, strengthening of those towers, the water and ventilation towers, with an interior lamination of concrete, and internal strengthening of the Peace Tower's piers and spandrels with post-tensioned rods. So my next few slides, I'll speak to each of these upgrade measures individually. So starting with the seismic isolation. Although seismic isolation has been used many times before to protect heritage masonry buildings, as far as we know, this might be one of the first examples of its application in a moderate seismic zone. And that's likely because isolation is often considered, at least anecdotally, to be quite expensive to implement relative to the benefit that is received in a moderate seismic zone. However, we've found that not to be true for our building. What we've found is that with seismic isolation, we get beyond a critical tipping point for our building where a large amount of the work we'd otherwise need to do is avoided. In particular, we avoid the need to strengthen the building's walls, and this is particularly advantageous given the difficulty of working around the building's heritage finishes. You can also see why isolation is so effective by examining the site's seismic design spectrum. It has a very rapid reduction in seismic force with increasing period. And this is actually a fairly common characteristic of many moderate seismic zone spectra, particularly at rock sites, which actually makes them quite well suited to seismic isolation, since the opportunity for force reduction with a shift in period, which is effectively what implementing a seismic isolation system does, is very large. In addition, for our building, the isolation system also serves to limit the accelerations imposed on the building's heavy architectural components, like those vaulted stone ceilings I showed earlier. So here's a summary of what our isolation system will comprise. We'll need approximately 580 bearings, and they'll be a combination of natural rubber, lead rubber, and flat sliding bearings. The diameters will range from approximately 575 to 775 millimeters. And their height will be quite compact at only 350 millimeters. This will give us a maximum system share of about 3.3% of the building weight, which is a huge reduction from our fixed base building starting point at 39%. And this max system shear is expected to occur at a max displacement of 95 millimeters. So this is really quite a unique isolation system design, particularly when compared to the systems used in high seismic zones. Specifically, the max shear of 3.3% W is a very low shear. Also, the maximum expected displacement is quite low as well. So what a system like this requires is a very low post-yield stiffness, sometimes called the second slope stiffness, to achieve that optimal force reduction, as well as very careful selection of the characteristic strength, which is akin to the sort of yield strength of the system. The verification of the system performance, we've been performing nonlinear time history analysis, which is required by the Canadian code. We've been using 2 suites of ground motions with 11 records in each suite, where one suite has been scaled to match the short period range of our design spectrum and the other, the long period range. Since we've invested all this effort in the nonlinear time history analysis, we've also been using the results of that analysis to derive floor spectra to help inform the non-structural component seismic restraint design. You can see our floor spectra on the right there, and it exhibits 2 peaks, as you would expect. The first is where component frequencies are matching the fixed base frequency of the building, and the other peak is roughly coinciding with the effective period of the isolation system. It is a very big reduction in the horizontal accelerations relative to the fixed base condition, which is very beneficial for reducing the amount of work needed for seismic restraint of all those heavy components. It's worth noting, though, seismic isolation doesn't reduce vertical accelerations, and that is a key consideration for a lot of suspended elements. With regard to how we're going to implement the isolation system, the bearings will be located in the basement space at the underside of level 1, which is just below the exterior grade level. We're constructing 1200 millimeter deep transfer beams above the bearings, which will permit a bearing spacing of approximately 4 meters on center. Since our isolation plane is below grade, we need a perimeter movement space around the building, which is sometimes referred to as a seismic moat or rattle space, which will be hidden below the exterior landscaping. A unique consideration for our project, since we're in a cold climate, is to make sure the detailing of this perimeter movement joint minimizes any impedance that snow or ice might impose. We also intend to isolate the peace tower on the same system as the main building. And that will require a 2-meter thick transfer raft to be constructed around the tower's existing piers. That raft will then be connected back into the main building's level 1 floor diaphragm. And also, since we have a different dynamic response between the peace tower and center block, we will need to introduce a small movement joint above the isolation plane between the tower and the main building to relieve the stresses that would otherwise be induced. So moving on to the seismic strengthening of center block's hollow terracotta tile floor diaphragms, We're going to remove the existing low-strength cementitious fill that currently overlies terracotta tiles and replace it with a 60mm thick ultra-high performance concrete topping. And the UHPC topping will be connected to the building's masonry walls with drilled and epoxied rebar dowels. It is quite a thin topping. We don't have the luxury of installing a really thick topping because we don't want to interfere with all the existing finishes. But we do think it's sufficient, and in large that is because of the reduced diaphragm demands afforded by the isolation system. And we've actually been fortunate to have the chance to experimentally validate the effectiveness of this upgrade approach with a test program conducted at the Canadian Research Council. We tested both the existing condition and two different upgrade strategies, one using the UHPC topping and the other using steel cross bracing positioned below the floor. What we found was that whilst both approaches do provide strength and stiffness enhancement, the underfloor steel cross bracing did require some initial deformation and damage to the terracotta tiles before it could activate, whereas the UHPC topping provided an immediate strength and stiffness enhancement, primarily due to its really excellent bond to the underlying terracotta. So coming back to those towers I mentioned earlier, they're shown here, these 4 towers at the rear of the building, known as the water and ventilation towers. And although retrofit of the building with an isolation system generally avoids the need to strengthen the building's walls, we do still need to strengthen these towers at the rear of the building. The main issue being that these large macro architectural elements impose quite a high local demand on the building, and unreinforced masonry is not particularly sympathetic to high local demands. The issue is compounded by the fact that the interior of these towers are essentially just continuous vertical voids that don't have floor slabs inside the towers. So their connection to the surrounding building is quite poor. So our upgrade approach solution for these towers is to create essentially a rectangular concrete tube inside each tower by lining all 4 sides of their interiors with a thick lamination of reinforced concrete, which we can then in turn connect that lamination to our surrounding floor diaphragms with drag bars. So finishing up with the Peace Tower, although the Peace Tower will be base isolated on the same system as the main building, due to its longer fundamental period, which is about a second compared to center block, which is about 0.3 seconds, fortunately, the force reduction we achieve by base isolating the Peace Tower is a lot less. With isolation, we reduce its base shear by about 50% relative to the fixed base condition. However, that's not quite enough to get us to 100% of code. So we also intend to reinforce its piers and spandrels with drilled and post-tensioned steel bars. So to wrap things up, what are some key takeaways from our experience so far with this project? Well, starting with seismic isolation in a moderate seismic zone, we do believe it can be a cost-effective seismic upgrade solution for short period buildings in moderate seismic zones, particularly if there is a strong desire to reduce superstructure intervention. However, it's optimized application does require a system with a very low post-yield stiffness. Also, since the targeted maximum system shear will be quite low, extra attention needs to be paid to details that might inadvertently increase the system breakaway force. Things we've learned about the hollow terracotta tile floors. Well, our experimental testing has demonstrated that it's possible to upgrade these floors and retain them in place. And in fact, a relatively modest application of a well-bonded topping connected to the surrounding walls can provide a significant seismic performance enhancement. Finally, I'd like to take a moment to thank the entire team that has contributed to the development of the Canadian Parliament seismic upgrade design. It's obviously a very large, very complex project, and it has a correspondingly large team of contributors. There's too many people to thank individually, but WSP would like to recognise the terrific support we've received from our sub-consultants, Wilsinko, SIE, and Farrell LCSO. All right, well, that's all I have. I hope that was informative and enjoyable for everybody.
Many thanks, Dave. Yeah, thanks a lot. It was so gripping that I couldn't get up to turn on my proper light switch. So you've just got this gloomy lamp here. But yeah, I think we've got a couple of questions coming in, but we will save all the questions to the end, and we'll go straight along with Jared. I don't think we've got a facility for applause here, but you can imagine folks clapping at home. Yeah, and Jared's modeling for us. Swanan, you were going to say something?
Yeah, one note, Damian, sorry. Whenever you are typing questions, can you please also type your role as well with you and current role and affiliation? That would be great.
Yep, thanks, Swanan. Swanan's put some instructions in the chat there to follow when dropping your questions in. Okay, so I think Jared, over to you. Don't forget to unmute.
Yep, sorry, I did that in the wrong order. Let me try resharing. All right, can you all see that, I think? Right, so thank you, Damian, and thanks for that, Dave. That's fascinating. I have a bunch of questions for you after this. As Damian mentioned before, my presentation is not on a specific retrofit project. It's more so about the interactions that we've been having in New Zealand with what is effectively quite an extensive national retrofitting program that has been going on. So it's a bit of an overview of what's been happening at a national level. Just so you know who I am, my name's Jared from a company called Beca. We're based out of New Zealand, but have a presence throughout Australia and Southeast Asia. And as you might imagine, for a company based in New Zealand, we spend a large proportion of our time dealing with earthquakes and their consequences. I spent the earlier half of my career over in Europe, working on a number of projects in the shakier parts of Europe. And then I moved back to New Zealand after the Christchurch earthquake, where I've been involved in various different projects, particularly in base isolation space, in timber and earthquake engineering space. And then a lot of my time has been spent on seismic assessment and retrofitted buildings. These days, it's probably well over half my time is on that space. And as a result, I spend a great deal of my time moving from those assessment works to talking with clients about seismic risk advice and how they can manage their portfolios to reduce seismic risk overall. And that's kind of what leads into this talk is the experiences with clients and how they have been dealing with this. And so this presentation could be seen as a little bit of what happens when a whole country starts talking about earthquakes, which is really the space that New Zealand's been in for the past almost decade and a half now. So I'll give just a very brief overview of seismic assessment in New Zealand, a couple of the bits that are very relevant for those discussions that have been happening. And then I'll talk through both the legislative and the market responses to it. How the public and engineers have been engaging with each other on it, and in particular how we've been dealing with some of the changes in engineering knowledge that have happened over this process and some of the complications that can arise from those changes. So New Zealand's seismic journey is reasonably comparable to other jurisdictions that have large earthquakes. We've been on a gradually improving course in terms of seismic design. Ours really started with an earthquake in the 1930s, where we introduced a very basic requirement to design buildings for lateral loads. And in the 60s, really, our modern seismic design processes started. So the introduction of capacity design and ductile detailing, which was then codified. So we see this step change in the resilience of our buildings from around about the 1960s, and then a gradual increase in performance beyond there as there were improvements made to our codes. Our first seismic assessment guidelines came into place in 2006, although we're not especially widely used at the time. And then in 2011, we had our first big game changer, which was the Christchurch earthquake. So this was a large event. There were 185 people lost their lives, significant damage through the central city in particular. And at this stage now, so 10 years on, Christchurch is where I'm based, and large portions of our central city have now been rebuilt. It looks very different to what it once did. This event, as you might imagine, significantly raised public awareness of earthquakes, not just in the area, but throughout the whole country. It very rapidly came to the fore in much the same way as people now understand that pandemics really happen. People in Christchurch and in New Zealand have moved from a position where earthquakes are a theoretical thing to a very real part of what can happen in their lives. Now, if that wasn't enough, 5 years after that, we had another bigger earthquake. This was in Kaikoura, in between Christchurch and Wellington, so in between our second and third largest cities. The two images at the top are representative of what happened around the epicenter, which was a great deal of land damage and infrastructure damage. Thankfully, only 2 lives lost in this one because it was in quite a rural location. But a lot of the earthquake force was projected northwards towards Wellington, and the images in the bottom are from the Wellington CBD. There were no lives lost in Wellington, fortunately, despite some of those, despite in particular the image on the right, which is the collapse of a precast panel inside a building. But there was a lot of building and infrastructure damage. And so this coming quite hot on the heels of the Christchurch earthquake has really ramped up the public awareness that not only can earthquakes happen, they are going to happen, and they're going to happen again. So the ramifications of that in a general sense for New Zealand have been, first and foremost, that the public now considers earthquakes to be a priority for them when they start thinking about buildings, particularly commercial buildings. And that flows through to expectations of tenants, of corporations who are representing those tenants, of building owners, and so forth. Our government has responded to that with legislation, which I'll get on to momentarily. And the engineering community has then further responded with a lot of research that's been going on and also additional guidance. So the legislation that came in place has a couple of very particular characteristics that are important for the subsequent interactions that the engineers have had with our community and with buildings. The act that was put in place, we call the Earthquake Prone Buildings Act as shorthand, because the full name's a bit of a mouthful. And it does a few key things. First of all, it defines an earthquake prone building. And it defines that as a building that can cause a risk of loss of life at ground shaking that is 1/3 as strong as our current design level earthquake. So that's become really quite important, this idea of ground shaking at 1/3 the strength of our design level earthquake. If your building is below that, it is considered earthquake prone. The Act sets up timeframes for which these earthquake prone buildings must be retrofitted, and those timeframes are between 7.5 years and 35 years, depending on the geography, effectively depending on the risk. It sets up a means for the local authorities to require seismic assessments to be undertaken. And it requires that a more fulsome methodology is established to identify these earthquake-prone buildings. So to identify these buildings that fall below the 1/3 or the 33% threshold for a new building design. Now, the methodology that was developed, and it was a year after the Act, is what we call our seismic assessment guidelines, or often here just the guidelines. And you can think of these as very comparable to kind of our new building standards. They're larger probably than our new building standards. There's a lot of information in there. But perhaps the most critical feature of these guidelines is they introduced a term called a percentage of new building standards, so a percentage MBS, which has become very widely known throughout New Zealand, and it's effectively a scoring system. So it scores the buildings against the current design standard, the idea being that you can use it to identify buildings that are below this 1/3 threshold, below the 33% threshold, and they are the buildings that are then more vulnerable. They're classified as earthquake-prone buildings, and they go through that legislative system. Importantly, the scoring system that we engineers put together to help evaluate earthquake-prone buildings is a very, very simple scoring system. It is a single number that is given to a building, and your building at the end of this assessment process gets given a score of, let's say, 60% MBS, and that is a known and recognised score, and that becomes important. So what happened after we released this process in the guidelines? The first thing that happened is what we all hoped and expected would happen, which is that a great deal of the more vulnerable buildings started getting assessed and started getting strengthened. I'm not going to go through the detail of any of those, but to give a few kind of key examples, a lot of institutional organisations, universities, hospitals and so forth started going through this process, started finding their older buildings. They had a lot of buildings from the 1960s and that were more vulnerable. What you're looking at here is not the nice roof in the front, but actually the building at the back is a classic 1960s building, which has been retrofitted and strengthened as part of this development at the University of Auckland. Similar things happened in commercial buildings. So this is just one example, but there's been many, many commercial retrofits that have happened. I put this one up because for those who want to know more about the technical aspects of some of the retrofitting in New Zealand, there's been a number of papers written on this building here, 8 Willis Street, which some of my colleagues in Wellington did. It's a very complicated and sophisticated strengthening scheme, and if you want to delve into some of the technical details, I'd invite you to have a look through that particular one. It's quite an interesting retrofit project. But it is representative of the broader suite of commercial strengthening. There's also been a lot of work on heritage retrofit. As Dave's shown in his presentation, some of these older buildings, the URM buildings, are by far and away the most vulnerable buildings, very often get classified as earthquake prone. This is one that was just completed recently down the road from us in a memorial hall at Lincoln University, which had also been quite significantly damaged in the earthquakes. And the final example is perhaps the least exciting seismic retrofit project that you might see, but one that I think is very important. So this is a random car park that I parked in a few days ago. And I put it up here because you can walk around Christchurch and most places in New Zealand now, and you will see seismic retrofitting in many buildings, especially many older buildings. And it has become what we hoped it would be, where a large proportion of our buildings have been assessed, and a great deal of those have then been retrofitted where they've found to have vulnerability. So we're in a situation where we have a lot of this retrofitting happening. However, there's been a few other things that have happened that are perhaps not quite what we might have predicted, and I think are worth highlighting. So first thing that's happened is buildings got placarded as part of the system. They got effectively a warning sticker put on them if they were earthquake prone. That's been good and bad. It has certainly prompted action on a number of these buildings, but it has left certain buildings that are quite difficult to retrofit with quite a stigma on them if they have one of these placards. The next thing that happened is the scoring system that we pulled together as a useful technical tool for us to determine these earthquake-prone buildings has really grown legs of its own. So this simple scoring system of effectively 20 to 100, which is how we score it, has been picked up by non-engineers across the country. And they see it I would say as something akin to how many people see, say, a Michelin star system or the star rating on your fridge. It's a very simple number as far as they're concerned. The higher number is better, the lower number is worse. And the general public has taken this and run with it, with a number of flow-on consequences for how we interact with them and how we deal with our buildings. The first immediate consequence of this is suddenly there's a huge engagement with structural engineers compared to what there was before. Because when we've presented people with this simple score for their buildings, the first thing they want to know is what does it mean, and tell me more. So structural engineers have spent a great deal more time than we previously have, talking with both the general public, but also with building owners, with those responsible for buildings, with boards and so forth. So we now spend a lot more of our time engaging with organizations at the highest level to help them understand their buildings and what they should do about it. And we're often now the first point of call, particularly on existing buildings rather than architects. Other industries have then started to pick up on this. So the insurance industry, first and foremost, for those who interact with the insurance industry, they are, generally speaking, very savvy when it comes to risk. They're pretty good at understanding these things, and they have grabbed onto this scoring system in a relatively sophisticated way to help them understand buildings better. And that in turn, as it has certain impacts on premiums and so forth, tends to affect the broader market. And I would say that interaction with the insurance market, in my view, has been a relatively positive one. It's been providing them better information than they would otherwise be able to get. Where it's become a little bit more fraught is the interaction with the real estate market. So the real estate market has also picked up on this very simple scoring system. But for those who interact with the real estate market, they are not as sophisticated in their understanding of risk. And this very simple scoring system has been used, but it's also, I would say, in some cases been misused. It's certainly been used in cases as a promotional tool. It has resulted through tenant demand for buildings that are more robust and more resilient in strengthening, but the tenancy market and the real estate market tends to drive change at the higher end of that market rather than the lower end. And so while we as engineers are wanting to address our most vulnerable buildings, the real estate market and the tenants who can afford to influence the real estate market are tending to want to occupy the best buildings. So that's tended to lead to capital being invested in buildings that are relatively resilient, becoming more resilient, rather than the more vulnerable buildings being taken to a modest level. So it has enhanced public interaction, but it's come with some caveats and some difficulties as a result. And the last area that this scoring system has overlapped with in quite a difficult way is our health and safety legislation. So our Building Act, like those all around the world, is based on acceptable levels of seismic risk. And we have this underlying principle that there's a certain level of earthquake you can design for, but at a certain point, there's just only so much you can do. And we have a general approach to try and reasonably reduce the seismic risk in New Zealand through the Building Act type approach. Health and safety legislation is different. It says when you see a risk, you have obligations to try and eliminate that risk and to do so promptly. And these two systems don't really mix very nicely together. And that's caused quite a lot of stress and maybe distress for those responsible for safety of occupants of buildings. There is guidance that's been put around to try and just calm people down to help them understand that seismic retrofit work is a long-term process. But there have been a number of examples where buildings that were not dangerous, but were classified as earthquake prone, so have a level of risk, have been evacuated despite or against the advice of various experts involved, saying there wasn't a need to evacuate. They've been evacuated effectively on health and safety grounds. And so that's a real difficulty that has come out of this. And we haven't really cracked it, I would say, as a country. We're still in that process of trying to find a way to navigate between this health and safety risk and the seismic assessment risk at an engineering level. The other key complication that we've had as a country is dealing with engineering change that's happened since the implementation of the legislation and the guidelines. So from a legislative perspective, that act is locked to 2017 when it was released. And the government has made very clear that they do not intend to change that they want 2017 to be a line in the sand, that everything can be compared to, and they don't want to be moving the goalposts on building owners. The problem is, whilst the legislation can stay locked, the market-related drivers that have arisen out of this do not generally stay locked. Tenants usually want their building to be assessed to the latest information rather than historic information. And there's been a number of changes in both not our knowledge of local seismicity and of engineering that cause some challenges with that. If we look at seismicity, these are the National Seismic Hazard Models from New Zealand. The previous one on the left here, the 2010 model, is the one that informed the standards of the time and informs the guidelines that were published in 2017. The latest one, 2022, is shown on the right, and what will be immediately noticeable is the very large increase in ground accelerations. This is for our design level earthquake that occur in some parts of the country. So Wellington is at the very bottom of the North Island, there where it's gone up to almost 1G. It's about a doubling of the seismic accelerations in Wellington. And there's a bit of debate about this, but there is certainly a very real increase in those seismic forces that we are dealing with when we start looking at the new hazards. And so we start to run into this problem when now our legislative requirements are based on the old accelerations, but we know, or the engineers know, and because we have this very engaged community, they know that actually the seismic risk is higher than what was looked at previously. And it's a real struggle to work through that and untangle it. It's difficult for engineers to do that, and it's much more difficult for non-technical people to work through that. There are also a number of engineering changes that have happened. As whenever you get a big earthquake, there's a great body of research that happens. If there's any academics on the call, their entire focus is around determining these areas where engineering is not sufficient, getting better information to us and promoting these engineering changes. But these changes can be difficult to deal with. So we have a particular issue in New Zealand, which is hollow core flooring. This is a precast concrete flooring. It's extruded in these kind of long units, and it's mostly unreinforced. In particular, the webs are unreinforced. So it's like maybe perhaps a more modern version of the terracotta floors that David presented. But there are some issues with these floors, and they were used very widely through the 80s and 90s in New Zealand. There's been some issues known about them since the Northridge earthquake back in the late 90s, I think it was. And there's been various retrofits that have happened over time, often little shelf angles that get put on here. So the car park example that I had previously had these shelf angles put on. But what we found is that there were unexpected failures of these flooring systems that occurred, particularly in the Wellington earthquake. And there's been a very large body of research done on these floors. So for those who want to know more about that, the Recast Floor Project is the name of that body of research, which was a large collaborative effort between the major universities in New Zealand, government with government funding, and also some industry partners in it. But if you have a look for this Recast Floors project, you'll find a great deal of information on it. The CSOC, the Structural Engineering Society of New Zealand, have published a standalone journal of a couple of hundred pages, I think, that effectively captures all this research in one place. There's a number of issues with it. One of the biggest ones we have found is what's been termed a negative moment failure, where the floor unit, which you can see horizontally across here, has the beam, which is on the left here, rotating away from the floor unit, and you get the shear crack forming away from the supports. So this has got one of these shelf angle type supports here, right next to the beam, but the shear crack is happening some distance away. And what's actually happening is that topping reinforcing is causing that end block to act as a rigid unit. The weak link is actually out beyond that topping reinforcing, so it's causing a loss of gravity support out towards the middle of the unit. So a real problem, and these floors are very, very widely used. Now that's one example of the sort of engineering change. But what that means for our clients, I'll talk through by an example of one specific client. So this is the cityscape of Auckland, our largest city. One of the clients I've been dealing with for the last 10 years or so is one of these buildings. I won't say which one for confidentiality reasons, but their story is very similar to many major building owners in Auckland and in Wellington in particular. And they, as diligent building owners back in around about 2017, when the guidelines were released, came to us and said, hey, can you assess our building? Tell us what we need to do. We worked through that. There were some weaknesses in those buildings. They said they wanted to achieve an 80% NBS rating, so quite a high rating. And we worked through that with them, did a bit of diaphragm strengthening in some localized areas and a few other little pieces of work to get it to that point. They were very happy with that and moved on. Several years later, a tenant came to them who'd been given advice by a real estate agent, one of their advisors, saying you need to ask about hollow core floors because there's been changes in hollow core floors. And our client came back to us and said, what's the deal with these hollow core floors? We said, well, by the legislative requirements, actually they're not covered, but yes, there has been this new knowledge that's come out. We can have a look at them for you. We had a look at them and we found that on their particular building, in some areas and some levels, and it's a function of detailing and various other things, there were issues with hollow core. We said, well, actually, if we were to assess it to the latest information, to the latest version of the guidelines, it would score lower than the 80% that you wanted. And so that client has effectively been forced due to real estate market drivers to go and re-strengthen parts of that building through no fault of their own, just because knowledge is evolving. They were early adopters of this, jumped into it early, and then as changes come along afterwards, they've had to go and do a second round of strengthening. And you can imagine the sort of challenges this causes. It can be very difficult clients to do. It can be very difficult for engineers to understand this. Most clients, most non-engineers expect that structural engineering doesn't change, that structures are pretty well set. And following these conversations, we also had to raise with the client, by the way, we're also having changes to our seismicity. And now, as it turns out, Auckland is not really strongly affected, so that wasn't a particular issue for this client. But for clients in Wellington, they're also getting told, well, actually, we were designing buildings for here, we were assessing buildings for earthquakes at this level, and now actually we think the earthquakes are going to be at this level, and you've got another new problem to deal with. So whilst it's been fantastic in my view that we've implemented this scoring system that gives very clear visibility, it's also made it very, very difficult for both for engineers, but particularly for non-engineers to deal with changes that have happened after that point. And so my summary of the key lessons, I guess, from the process that we've been going through as a nation over the last 10 years is first and foremost, we shouldn't lose sight of this. In my view, having very clear legislative requirements are highly effective at approving the most vulnerable buildings. And we can walk around any city in New Zealand now and we can see that our vulnerable buildings, our old masonry buildings, our buildings from the 1960s, 50s and before being strengthened. A simple seismic scoring system, and I will emphasize simple. I think it really has to be a single number for it to be, for the general public to be able to engage, can significantly increase public engagement with engineering. We've definitely seen that. I think those who are familiar with systems like Green Star, where they have got widespread traction, can see the results of a very simple system. You could probably also see the challenges from a technical perspective that boiling a complex building down to a single score does come with challenges. That once you establish that high public engagement, there's a really good opportunity for engineers to be heard and to get our voices across. There is also the opportunity for us to be misheard. This information, once it is away from engineers, once it is in other industries, often comes without the nuance and the caveat and the detail that we are able to provide when we're involved. And because it's simple, that information does travel and it does move away from us. And in particular, once the public has engaged with engineering, once they have got to grips with this, this very simple understanding of building vulnerability, once change occurs, that can be very, very difficult to manage. It can be difficult for us and even more difficult for them. And I don't think we've cracked it as a country yet, although we have maybe some practice now. And it might be interesting to reflect on in other locations where people are starting to bring in these kind of clear engineering numbers or rules, what that does look like when change occurs. Thank you very much.
Thank you. Sorry, just trying to get my video. There's this one, and I think you're going to take over for the Q&A.
Yes, thank you both for the talk. And I think we have got few questions already in the chat, and feel free to keep asking questions and we'll take as many as we can. So the first question is from Dave, and it is also for David. What is the vertical spectrum for the center block? I think it's the spectral acceleration in vertical direction.
Yeah, that's a good question. So we actually had a site-specific vertical spectrum developed for us. Often, sometimes people simply use 2/3 of the horizontal spectrum, but we found that wasn't really appropriate for sort of the lower moderate seismic zone that we are. That being said, it was a challenge to get a spectrum developed. Being on the lower moderate seismic zone, there's a lot less data and records available on which to sort of base these judgments. So in the end, we did get a specific vertical spectrum developed for us by some seismologists in Canada. And we also had to use a specific vertical scaling factor for those records, rather than simply using one uniform scaling factor, which is pretty common practice to do all three components of the record. We found that was overly punitive for the vertical accelerations.
Right. So going in the order, the next one is also for Dave. It's from Andrew McDonald. Is the UHPC reinforced other than the connections to the walls? There appear to be weights placed on the top of test specimen. What was this for?
Yeah, so I guess the goal of the experimental testing is really to establish how far can we deform these units before we lose the vertical load carrying capacity, because that's what everyone really cares about, not really how much load it can take. It's does it stay standing up vertically. So the weights on the specimens are basically just to mimic the dead weight of the topping and the other finishes. We did test the specimens to see whether is the weight actually beneficial or negative, and because of the sort of wedge-shaped geometry of the units, they do actually have a tendency to want to pop up a little under seismic deformation. So the vertical weight actually helps. That's what we established. It's pretty interesting. In terms of the reinforcement question, the UHPC does have a very high direct tensile strength, in the order of at least 4 to 5 MPa. So many instances on short diaphragm spans, we don't actually need much chord reinforcement. However, whenever you have openings that you need to work around, the collector bars are something you can't get away from. So essentially, our topping will be the dowel bars into the walls plus collector drag bars, and then a ton of steel fiber in the UHPC as well is what we need. And we can't fit much more than that in a 60mm topping.
Okay. And another question from Andrew McDonald is the low yield stiffness. Does it influence the wind response of the building?
Sorry, what was the first question? Stiffness.
The low yield stiffness
Yes.
And does it influence the wind response?
Yeah, so we have sort of an initial stiffness of the system where it's quite stiff, and we want that to resist wind loads and keep deflections very small under wind loads. So the Canadian Code requires us to not have any sort of activation of the system for at least 1.5 times the ultimate limit wind. So the initial stiffness is really provided by the bearings with the lead cores and the friction sliders, plus some of the elastomeric there. But that's pretty much how we tune the system, make sure we have that the characteristic strength is high enough to at least not have any chance of activating under wind.
So I think one more related to that is post-yield stiffness. Why is it important, the low post-yield stiffness?
Well, the lower that is, the lower you'll be able to get your maximum system shear. If that is too steep, then you just won't get it down to the number that you'd like to.
And then the last one is, I think, about how long is the retrofit going to take, the construction of the retrofit?
Well, it's as I sort of alluded to, it's actually part of a much bigger rehabilitation program. So the project actually kicked off in 2017, and the building was emptied in 2019. The occupants were relocated to another temporary Parliament facility. So the retrofit involves also digging a big underground welcome center below the building, down about 23 or so meters into the rock. So that's actually the key driver on the project time that it's going to take. The actual retrofit work associated with the seismic upgrade is is much smaller than that overall program.
Okay. Now I'm moving to Jared's presentation. The first one is from Bernardo, who's a design engineer at Walter P. Moore. Are there any ongoing discussions about changing the earthquake-prone building index? Does the government provide any financial assistance for the retrofit?
On the first half of that, yes, there is actually currently a review on the process, which has only just started. We're not sure what will come of that. But the question of that review is really, is the bar that we have set of this 33% the right bar, or should that be adjusted to mandate it? And I guess that is partly because in terms of financial assistance, there isn't much. There is a little bit that is available because the groups who are struggling the most with this tend to be residential homeowners of shared apartment type properties. So generally it's worked pretty well for commercial properties and for institutional organizations, whereas you have a single owner of a building, but when you have shared ownership, it's really quite difficult to deal with. So it's being looked at probably in light of those people in particular who are the ones who find it hardest to deal with this. So I think short version is yes, there probably will be some updates to this going forward.
The next one is from Kiran Sagar. It's about the scoring, the percentage NBS scoring being used. Can it be used for longer term asset management type approach, similar to landslide prevention measures in Hong Kong?
Yep. I'm not familiar with the landslide prevention measures in Hong Kong, but certainly the percentage NBS scores are used in an asset management context. So after we do the strengthening, we'll certainly update those scores. That's key part of what the clients want to see. Is it was 30% building and now it's an 80% building. And it's also used with the more sophisticated clients to help prompt more widespread discussions about how they manage their assets. So it's a bit of a start for them, and then once they're into it, they will usually delve into a more sophisticated understanding of their assets for the sophisticated clients.
Next one is also for you, from Miguel. What are the lessons from how Christchurch is being rebuilt, and especially with respect to concrete versus steel debate?
So concrete versus steel, I don't know that there's a lesson for the world. There is a very specific change in that we were a heavily precast concrete building before the earthquake, and we are a heavily steel building now. I think that is a particular response to some of our precast detailing, which wasn't very good, and the general market trends maybe specific to Christchurch. Broader trends, I would say there was also a very strong trend towards either low damage systems or repairable systems. So a lot of base isolation went into the immediate rebuild driven primarily by tenant demand and systems like replaceable active links on EBFs and BRBs and elements that could be replaced went in. So that was certainly a trend we saw. It's a trend we would certainly promote around the world, but that has tended to peter out as time has passed and memories have faded.
Next one is for David, about design retrofitting plan. So how long did it take for the whole design plan, I would say?
Well, I guess we are nearing the end right now. So that timeline was about 8 years. However, the initial part was actually a substantial investigations period where we're trying to, take the building apart and understand how it was built and what the sort of inherent material strengths are. So initially we were doing that type of investigation work with an occupied building, so it was all happening at night. So that certainly is a slower start when you do that. But we were really, I guess, up and running at full speed, probably from about 2019 or so. So roughly about 5 or 6 years. Again, that's not though the seismic upgrade design timeline. That's really some of the other types of design that goes into the underground welcome center. The understanding the initial assessment and then coming up with the preferred approach, the seismic upgrading, was probably only 2 to 3 years, I would say. And then we've been slowly working through the implementation after that.
Can I ask a follow-up on that one, Dave? Well, I was curious, when you see these kind of presentations where someone presents so convincingly that, that the system that's been picked is sort of perfect for the situation, but it always sort of obscures all the work that's gone on behind the scenes to get to that point. I wonder just if you can sort of take us through a little bit the missteps along the way, or the different directions you might have taken things in the earlier design stages, or did you leap straight to a final base isolation?
Well, I won't admit any missteps, of course, but actually our client did ask us to do 2 full schematic designs. So we started with I guess what we called more of a conventional seismic upgrade design. And that really involved trying to strengthen the walls in some fashion with laminations of some sort. And then it was a full schematic design that we then worked through with our heritage professionals to understand the impacts to the finishes, and it was costed by the construction manager as well. And they put a cost and a timeline to it. And then we had the seismic isolation system design, and that one came out as a fairly clear winner. Interestingly, we sort of had to justify the preferred seismic upgrade design on its own merits, but in many aspects, it has more benefits than just the seismic upgrade, because with seismic isolation, it creates solution space for other parts of the project. For example, if you want to parts where we're adding some extra structure, vertical expansion on top of parts of the building here and there, that's a bunch of extra mass. It'd be quite challenging to do on conventional seismic upgrade context where you're already struggling to get it to a decent point. But with seismic isolation, we're bringing the forces down to such a low level that it becomes not such a big deal. So we can do things like that. We can do lots of openings in the floor plate for mechanical and electrical services because the diaphragm demands have come down. And almost those transfer beams in the basement that I showed that we need to sort of use to carry the weight of the building from its sort of continuous support system it has now to these point supports at the isolators. Well, we can actually use those concrete beams to sort of temporarily shore the building to dig the big hole beneath it. So sort of a dual purpose. So there's lots of extra benefits that come to that help us out, and I think it really was definitely the right decision to go to. As the fullness of time is shown, there's lots of other great benefits to it.
Right. So next one, I'll club two questions which are very similar, and they are for Jared. So how do you think the seismic retrofitting practice in Auckland will impact rest of the world, and also the rating system, how it can be applied to the other countries where the seismic codes are not very advanced?
Yeah, so in terms of how retrofitting will develop, I think what we have seen and will continue to see as the development is technological development, as there has effectively been the implementation of a demand to retrofit buildings in New Zealand. The suppliers have come to the party and they've started to provide products that weren't available previously and are generally better specifically for retrofitting. So for example, on URM, on masonry buildings, there's a lot of things like masonry screws that have come to market that weren't readily available before, that are now widely used. Those suppliers are starting to come to market now with retrofit options for these hollow core floors that have been very problematic for us to retrofit, but they are now starting to bring options to market. Kind of at the more sophisticated end, things like dampers, which were basically never used in New Zealand prior to this, are starting to get used more and more frequently for retrofit, because they can be very effective for retrofitting these old concrete moment frame buildings. In terms of application to developing countries, well, in terms of application elsewhere, I'd say the one characteristic of the system we have that I would very strongly consider for any other country is ours does not require full compliance with the current seismic codes. It sets a reduced bar for these older buildings, and I spend a reasonable amount of my time in my role dealing with clients outside of New Zealand who don't have that, and it's really, really hard for them because they have this immediate goal to get to compliance, and it's near impossible in some buildings. But actually, if you can get these older buildings to half of the current seismic codes, that gets rid of the vast majority of the vulnerabilities. And I'd certainly advocate for that. In developing countries where there just isn't the funds to do more sophisticated retrofits, to my mind, I wouldn't actually use an assessment type system like we have, or let's say the Americans have. I would just do targeting the vulnerabilities. There are some very clear vulnerabilities. Dave showed some right at the start of his presentation on that smaller earthquake that happened, chimneys and parapets and gables and things like that. Once you know what you're looking for, you can just walk around and look at them. And there's some very simple retrofits that are not engineered. They're just, plywood and bits of 2x4 to hold these things in and stuff like that. That'll do an okay job. And if there isn't the money, I would do that rather than, the more sophisticated stuff that we're doing in other places.
Okay. There are two more questions in the chat for Jared. I'll start with the first one. Let's see how long it'll take. Has sustainability been a factor in saving more URM buildings and so on?
In New Zealand, I would say the short version is no. I would say it's the opposite. I would say the system we have has encouraged buildings to be retrofitted, and there are massive sustainability benefits when you can reuse a building compared to building it new. So, and I guess the clarity of the process has facilitated those retrofits more than it might otherwise do. I think in other places where sustainability is a very strong driver, and I know from my time in the UK, it's a very strong driver in the UK. Then you have maybe the opposite overlay where you're trying to save these buildings for sustainability reasons or maybe heritage reasons, and it's let's say relatively simple when you don't have earthquakes, but when you do add earthquakes to it, it gets a lot harder, which Dave's presentation has shown, right?
And I think the next one, by Shugun, can you briefly explain how to obtain the NBS score? If you can refer to a publication.
I think
that's
specifically
okay.
for a complex building, though, the
Yeah.
question is.
Yeah. So I won't go into the detail. There's 1,000 pages of detail on it, so it's quite a complex thing. But a couple of kind of the key characteristics, and I guess in relation to judgment, yes, there is a component of judgment that is required. In many ways, an assessment has similarities to a new building, but you don't have very good information about what's going on, and you don't get to control the system. So you don't get to put in a nice failure hierarchy. You have to try and figure out what's there, and quite often quite small differences can make huge changes. The actual score itself, one of the quirks of our particular system is you assess all the various parts of the system and you score every element individually. So if we took Dave's case, you would score the walls, you would score the floors, you would score the ceilings, you would score each of those towers. Our system then takes the worst scoring element and it allocates that as the single score. And that can cause complications. And so you could have what's quite a good building with a handful of poor elements on it, and those poor elements could drive down the score. Now, that's one of those things that requires a more detailed conversation with the client. And if you can explain that to the client, you can say, well, actually your building's 50%, but you've got some parapets over there that are 20%. Let's sort of the parapets, and then your building will be 50%. You're in a good place because that's removing those vulnerabilities, which is great. That's what we want. It can be relatively simple to do. And when the engineer's having those discussions, that's what will happen. When the information gets away from the engineers and you've just got the 20%, but it only is because of some parapets, that's when you get misunderstanding and confusion in the system.
I wonder, just thinking about one of your previous answers, Jared, I wonder with the New Zealand situation, the extent to which it's unique because of everything being compressed into such a short space of time. I suppose that happens after earthquakes in lots of countries, that there's a lot of action in that, but it really feels like so many of the market stuff, the public perception stuff, and well, yeah, mostly those things. And sorry, and the market proposing technological solutions, like, that's the sort of leg up that a new company needs is like a huge market for what they're doing. And
yeah, and I think we are quite unusual in this case. Like, so if you take Christchurch, a lot of Christchurch is just getting rebuilt, actually. So a lot of the effort in terms of retrofit is happening outside of Christchurch, in places like Wellington and Auckland, and I think we have the advantage of being a small country in this case, that we can move quite quickly to set these guidelines up. Set the act up, set the guidelines up. You can literally get the right people in a room and sort it out. So there's a disadvantage of being a small country when you're in business as normal mode. When we compare to, say, the very rigorous process that the Americans have with their standards, it's more sophisticated and a more smoothly oiled machine than we have. But when you're in crisis mode, we can pretty quickly adapt and set up these new things. And I think that's what's happened in our case.
Mm-hmm. Excellent. Swanan, what do you reckon? Should we probably call it a day unless there's anyone with a pressing question?
I've got one question for Dave.
Oh yeah,
if that's
I was
all
going
right.
to say, actually, why don't you guys have a chance to ask each other? Yeah.
Yeah.
Which is Dave, I've done a little bit of base isolation, and your system is, as you've highlighted, it's very important that it mobilizes at quite low levels of shaking. So that release point is critical, and you've highlighted the need for the moats, for instance, to do their job properly and not get filled up. So my question is really around that process of how you're ensuring that in two parts to it. One is what sort of testing are you doing on the isolation system to make sure that it reliably performs as you need it to? And also, are you doing anything with the client and with the operations team to make sure that some bright spark doesn't go along and fill up the moat with gravel? Because there's some really nice examples in Turkey of exactly that happening. So I wonder on both of those halves if you're dealing with those.
Yeah. Well, in terms of the testing of this system, so we are doing sort of following the American standards in terms of requiring prototype to be developed first and then rigorously tested at an independent laboratory. So we're currently actually working through that process for our bearing designs, and then assuming we reach a point where we're satisfied with the prototype testing, then we enter into the sort of production of the bearings as well as production testing. So there's the two levels of testing, production and prototype, which is very rigorous, and then the less rigorous production testing. So I think we, actually end up at a place where there's a lot less uncertainty with your seismic system because there is only 500 elements that basically define how it's going to happen, and you've tested all of them. So you know pretty well what it's going to do. We will also be able to take those results and actually rerun our analysis again at the end of it all to see that we have landed where we were hoping to land. In terms of the making sure all those details work out, because for sure if you visit other base isolation projects, you will inevitably find a few things here and there, handrails that cross the isolation plane, or the old metal garbage can that's anchored on both sides of the joints, and things like that. Also, mechanical electrical equipment is a big one, sort of things hanging in unistrut. So we do have to produce a operating manual for the building for the client, and we sort of do recommend that there sort of be the annual or semi-annual kind of walk-arounds by a structural engineer that knows what they're looking for, pretty much just to keep an eye out for that sort of thing, to say, oh, actually something's happened here. They've put this piece of unistrut from one side of the plane to the other. Through the course of the project, though, the design period, it really is sort of a constant effort of education. You have to sort of, every mechanical, electrical engineer and architect that you're working with, you have to keep educating them about how the building's going to move, and the necessary gaps and what it means if you're stepping the isolation plane, etc. So that is sort of a lot of investment and time that we have to do to get the whole team sort of moving in the same direction on that front. And I think we've been pretty successful. People have really embraced it and understand it, and so far so good. But we haven't yet implemented the system, so I guess stay tuned.
Mm-hmm. Conscious of time, but also with Dave's right of reply, did you want to ask Jared anything from his presentation?
No, other than very much appreciated comments around the difficulties of a single number system, because that is fairly common practice here in North America too. That gives it's just a percentage of current code or new building standard, I guess, using the New Zealand lingo. And certainly I've encountered the same issue where you can have two buildings that are both at 20%, but they are in very different places in terms of the amount of work that is required. And that's just highlights the importance of structural engineers being part of the conversation with the clients to sort of really nuance that discussion and say, 20%, but you do a little bit of work and you're going to jump up straight away. And that's a great story for a client. Or maybe it's not. Maybe you're just at the next component that's at 21%, and the one after it's at 22. So so there's thanks for those comments, Jared.
Fantastic. Well, I think that's a great message to end on. So thanks once again to Jared and Dave for really excellent presentations. We've had some appreciation already in the Q&A there, and yeah, the talk will have been recorded, so it'll be available on the ICU website at a certain point. Look out for SecEd events upcoming, and yeah, thanks again to the speakers.
Thank you, Paul. Thanks.
Great. Thanks for organizing,
Cheers
guys.
all. Yeah, thank you.
Yes, thank you.
Cheers, guys.
Yes.
Cheers. Yeah.